Hi, and welcome to Science with Armstrong. In this video, we're going to be doing some population math. Here are the three population equations that we'll be using. We have population growth, we have exponential growth, and then we have logistic growth. And on a general whole, if you're going to be using these, you need to be given the information, or you need to be given a way to figure out the information. So if you're not given carrying capacity or given a way to find carrying capacity, then you're not going to be using the logistic growth equation. So one of the first things that you should do is take an account of the information given to you, so that way you can choose the right equation to use for your population growth. Let's start with an example. Here is an example. There are 300 falcons living in a certain forest at the beginning of 2013. Suppose that every year there are 50 falcons born and 30 falcons that die. What is the population growth rate, including units? Interpret the value. The equation that we're going to use is the population birth rate. And that equation is dn dt, so the change in n over the change in t, which is what we are looking for, is equal to birth minus death rate. So looking at the information given, dn dt, so the change in population over change in time, is going to be 50 minus 30, giving us 20 falcons per year. So this is stating that every year 20 falcons will be added to the population. Let's look at the next part of this question. What is the per capita growth rate of falcons over a year? So this is for the entire population. If we want the per capita, we would need to take this 20 and divide it by the total amount in the population, and there are 300 falcons. So we are going to get 20 divided by the 300, giving us a 0.067 or a 6.7% increase. So now let's take a look at this population of falcons over the course of a couple years. In 2013, we have 300 falcons, and our growth rate is 6.7%. So here we've also figured out to be 20 falcons for the year. So in 2014, we are going to be starting out our year at 320, because I'm taking this 20 and adding it to my 300. If I wanted to find 2015, I'm going to take my 320, multiply it by my 0.067, and then add that number to my 320. So I'm going to get 341. Then I have 2016, and then I'll also do 2017 and 2018. I'm going to take my 341, I'm going to multiply it by the 0.067. Whatever comes out of there, I'm going to add it to the 341, and that comes to 364. Again, I'm going to take the 364, I'm going to multiply it by these 0.067. I'm going to add that number to the 364, and I'm going to get 388. And one last time, I'm going to take 388, multiply it by the 0.067. I'm going to then add it to my 388, and I'm going to get 414. Now, if we want to find the average rate of change of this population over time, we're going to do the change in y over the change in x. So the change in y is going to be the change in our population here. So our change in y would be 414 minus 300 divided by the time, so that's 2018 to 2013. And that's going to come out to, so I'm going to subtract those two, divide them, and that's going to come out to 22.8 falcons per year. So for the first year, it was 20 falcons per year, but when we do the average overall those 5 years, it comes out to 22.8 falcons per year. Now let's take an example of logistic growth. Here's an example. Kentwood, Michigan has a population of 49,000 in the year 2013. The infrastructure of the city allows for carrying capacity of 60,000 people. R max equals 0.9 for Kentwood. Or is the current population above or below carrying capacity? What will the population growth be in 2013? Here we need to use our carrying capacity equation. dN dt equals R max. Remember, R max is the per capita, so usually this is going to be a decimal point, and that's another thing to remember when you're doing even your exponential growth, that R max is going to be a decimal point on a general whole. Not always, but you're looking for that piece of the whole. Times N, which is your population size, carrying capacity minus population divided by carrying capacity. So dN dt is what we are solving for. Our R max is 0.9. Our N is 49,000. K is 60,000. Minus N, our 49,000. Divided by K, which is 60,000. And then when we do all this math out, I'll do this one first and then this one, and then multiply them together. Our dN dt, or our change over time, is going to be 8,085 people per year. So then when we're looking at the population size at the beginning of 2014, because remember 49,000 was for 2013, we're going to add this 8,085 to the 4,900. So at the beginning of 2014, our population is going to be 57,085. So we are getting close to that carrying capacity. So again, remember, R max is generally going to be a decimal point. N is the size of your population. If you are not given K, then you don't want to use this equation. You want to use the either Rn, either exponential growth or population growth. If it's just asking for population growth, you're probably going to want to use the B minus D, the birth rate minus the death rate. If they're looking for per capita, you want to take the B minus D and divide it by the total population, so that way you can get the per capita. And then lastly, just pointing back to R selected and K selected organisms, this is where this comes into play. So R selected is going to be having this growth rate change, where K selected is going to be looking towards this. And there's a whole big idea of how this math works for an R selected organism comparatively to a K selected organism. But I just wanted to point out that these are the numbers that are going to be changing this entire equation. So the R selected, this is where it's going to be manipulating this equation, and K selected, this is where it's going to be manipulating the equation. And that was population math.